Hello, our group consists of Victoria, Christian, and Bruno, and we will be presenting our work on the Internal Combustion Engine Lab so far. To give some background, Generative Energy Systems Incorporated has designed a generator based on a modular internal combustion engine. The engine can run either on compressed air or on propane fuels to work as a generator. We were tasked with determining the system parameters and the control for this new system. Firstly, we characterized the mechanical properties of the engine, starting by associating the shaft angle with the piston position. We then determined the work done on the flywheel by friction, after which we determined the inertia of the flywheel. In the second part of our experiment, we characterized the fluid's properties of the IC engine by determining the exchange of energy between the pressurized air and the flywheel. Lastly, we are asked to determine the control for the system for optimal power generation. The system has an encoder to determine the engine and motor shaft position and the force transducer to detect the engine torque. The engine was tested at different speeds with different flywheel masses and with the head on and off in order to fully characterize its parameters and control. In order to give you a better understanding of the processes in the experiment, shown here is an outline displaying all the subsystems in orange that have to be accounted for. You can see that the voltage from the force transducer and the torque from the torque transducer are put into a York regression from which the force transducer gain and the torque calibration offset are determined. These are then used to calibrate the transducers and provide us with a torque calibration model. From this now calibrated model, we can determine the change in the angular position and the average torque value. These values are then used to determine the work done by different subsystems of the engine. Shown on this slide is the modeling equation assumed for this system. It's important to note that only the angular velocities and the work of the motor are measured values. Some assumptions also had to be made here, such as that when the engine head is removed, the work of the air is negligible. Similarly, the work of the piston is negligible for high flywheel masses and/or for large ranges of numerical integration over the change in the angular position from A to B.
The only work that we can directly measure in this system, and the one that will help calculate the work done by the other components of the engine, is the work done by the motor. We can find this by finding the torque that the engine applies to the motor using a force transducer and integrating this over the angular displacement. So, we must calibrate this force transducer before each use. We calibrated the transducer by adding multiple weights of a known mass onto a moment arm of known length and measuring the voltage. Running a linear regression on these points gives us the correct gain for the force transducer, but we need to zero our calibration by collecting the voltage with no mass applied, known as the offset voltage. With this, we can reach our corrected calibration curve to properly measure the work from the motor. As you can see, the dramatic differences in the gain and offset of the curve between week 1 and week 2 show the importance of calibrating the transducer every week.
These are our results for the work of the friction done on the flywheel. This was determined by averaging the torque values at steady state and integrating over the change in the angular position. Since this is at steady state, the average torque values were simply multiplied by the total change in angular position, as indicated in the graphs with the red markings. As expected, the work on friction increased as the speed of the flywheel increased. Some assumptions were also made here, such as that the coefficient of friction was assumed to be constant under all the different RPMs.
To calculate the moment of inertia of the flywheel, we had to make some assumptions to eliminate variables from the main equation. We assumed there was no change in air pressure in the system since the head was open. We accelerated the motor from rest until it was at steady state, and we treated the work from the piston as negligible, as we just proved. Thus, we were left with the kinetic energy of the flywheel at steady state being equal to the sum of the work from the motor and the work from friction over the total displacement. Isolating iFly gave us a clear path to deriving this value here, shown on the right. It's worth noting that the flywheel assembly contains multiple rotating parts, such as the crankshaft. So to find the correct iFly, we ran a trial with the flywheels on and a trial without any flywheels, and subtracted the no flywheel value from the fully loaded value. Then we compared this experimental value to the theoretical equation for the moment of inertia of a disk. These are the results of the two trials. We found T friction by averaging the steady-state torque values before finding work from friction as we did previously. The work from the motor was found by numerically integrating the torque data over the full angular displacement using a Riemann sum. So all of the work from the motor is the shaded area here in each graph. As you can see, our experimental value is approximately 1 order of magnitude greater than the theoretical value. Moving forward, we will investigate the potential causes of this discrepancy.
Hi, Hi, so after finding iFly, we then determine work of air. We first add the head back onto the engine block, which is what introduces work of air. It is best to analyze each stroke of the engine individually because each provides us with different information needed to calculate that work of air. So let's start examining the intake. The valves open. First, we assume the flow losses are negligible as we draw on air, meaning work of air is equal to 0. Also, we assume work of the motor is opposite but equal to work of friction. Next is the compression stroke. The valves are closed. Assumptions are compression happens quickly, there is no heat transfer, thus it's adiabatic. Pressure on the piston in the cylinder is the same at top dead center or bottom dead center. We also need to remember that there is also air behind the cylinder at 1 atmospheric pressure. This then leads us to the theoretical equation that you see on the slide. From week 1, work of friction is less than 0. Since the volume decreases as we compress, we expect to see the work of air to be less than 0. Even with the work of air from the atmosphere above the piston being greater than 0, work of air for the compression stroke should be less than 0. The power stroke. The valves are still closed. Again, expansion happens quickly, so heat transfer is 0, still adiabatic. And we follow the same assumptions as compression. From week 1, work of friction is less than 0. Since the volume increases as we expand, we expect to see the work of air to be greater than 0. Even with the work of air from the atmosphere below the piston, work of air for the power stroke should be greater than 0. Lastly, we examine the exhaust stroke. Again, assumptions for the work flow losses are negligible as we draw on air, assuming work of the motor is equal to the work of friction at steady state. We found the volume of compression and expansion at the angular position. The volume is the sum of those three terms that you can see on the slide. The volume never reaches 0. This is due to the engine displacement where the piston head is sitting in reference to the top of the cylinder. It's sitting down inside there a little bit, thus causing that offset that you see in that plot. Currently, our team is still analyzing data for medium and high speed. Analysis was completed for the slow speed. First, we found the work of friction for the intake and exhaust stroke. Then we found the work for compression and the power stroke. When comparing the compression and power stroke for the theoretical equation, we see that the expectations of the work in the power stroke is opposite but equal to the work of the compression stroke. You can see that in the table via 22.24 joules. We expect to see the negative sign for the compression stroke since the volume grows less as we compress, and we expected to see the work of air for the power stroke to be greater than 0 since the volume increases. Since our theoretical equation showed us that the work in the power stroke is opposite but equal to the work in the compression stroke, it was expected to see the same for the experimental model equation. This did not hold true. It was seen that the compression for the experimental model was negative 23.04 joules and the power stroke was a positive 8.174 for slow speed. The sign conventions still hold true for the compression being negative and positive for the power stroke due to those increase and decrease in volumes. Thoughts on why the compression and power strokes are not equal but opposite in the experimental model might be due to making those ideal assumptions that no longer hold true. More analysis is required before coming to a conclusion. Again, we are still analyzing data for week 2. So in conclusion, week 1 was the removal of the head, the finding of work of friction in steady state, and determining iFly. Week 2 was also head-on. No pressure, no injection pressure. Work of friction was found from the intake and exhaust, and the work of air was found from the compression and power stroke. Going into week 3, we will be having the engine head on still, injecting pressure air to simulate combustion, and we should also see the engine doing work on the motor like a generator. Thank you for your time.